Hello everybody, welcome to lesson 5.1, which is a concept called work. It falls under the category of work, energy, and power, which is our chapter 5. In general, these concepts of energy are very important because it's one of the biggest crises we face right now. Most energy produced on this planet is done so with fossil fuels, and so to find better sources of energy, we first need to understand these basic physics concepts. In the video you're about to watch, you'll see that I wrote chapter 6 and I wrote 6.1. That's a mistake, so copy down the 5 and the 5.1. Again, make sure you write chapter 5 and 5.1. The 6's in the following video are a mistake. Thank you very much, and I hope you enjoy. Like many things in physics, this will be a mathematical definition. It is the product of force, displacement, and the cosine of the angle between them. Semicolon, because I'm going to add a little more. Product, so the definition of force, it's the product of force, displacement, and the cosine of the angle between force and displacement. Now conceptually, that doesn't do much for us, so I've come up with a somewhat conceptual definition. The change in an object's energy. The change in an object's energy. Now, we haven't learned anything about energy in this chapter, of course, because this is the first part, but you probably know a little bit about it. Most of you have learned that potential energy is by virtue of how high an object is. So if you raise an object upwards, you're giving it potential energy. You do that by doing work on the object. You can work on an object to give it potential energy, bringing it up here. The other type, kinetic energy, is about velocity. So if you work on an object, you could give that object some extra velocity and therefore increasing its overall energy. So that's what I mean by the change in an object's energy. Today, we're more focused on calculating work. The calculation itself is rather difficult. The math is easy. But there are some elements of it that get challenging. So here's our definition. Force times displacement times the cosine of the angle between those two things. Let's label those. Work is W. In parentheses, I'll put the unit, which is capital J. Capital J is the unit for work. You'll have to memorize that. F is a little tricky. It's one of the reasons it's hard to calculate work. F is the particular force being analyzed. Of course, that's measured in capital N for newtons. All forces are measured in newtons. Over here at S, we have displacement. Notice that it is no longer, S is a weird thing to use for displacement. The reason they use S for displacement is because we're already using D for distance. D is the variable for distance, and we can't use P like we did in chapter 2 because P is also momentum. So that's why we're using S. Finally, theta, Theta, is the angle between, I'm going to have to squeeze this in a little bit. Maybe watch what I write before you try to find space for it. the angle between vectors F and S. F is a force that points in a certain direction. So maybe we're looking at gravity. That means that F points down. S is a displacement that points in a direction. Maybe the object is moving down, so S would point down. I'll leave it there. So there's our definition for work. One more thing to add, I'd say, is the units. What's up with this unit here, J? Well, first of all, the unit for work should be newtons times meters, which it is, but instead we use joules because it's shorter to write that. So the unit for work, the official unit that we use, is capital Joule, and that's pronounced as joule. Joule. Or if you want to be fancy, you could say that it's Newton meters. I would say that Newton meters is well, it could be even more descriptive than that, so I'll just leave it there. So basically, joules is short for Newton meters. Try to remember that pronunciation. Joule, that's the unit for work. Okay, I think we're good there. Let's keep rolling. So in the next example, we're going to look at this concept here. The fact that theta is the angle between F and S. So we're going to see some examples of F and S vectors in this next example. So the prompt for this example is calculate work for each set of vectors. Calculate work for each set of vectors given that F equals 400 newtons and S equals 10 meters. Calculate work for each set of vectors given that F equals 400 and S equals 10, which units are newtons and meters respectively. We're going to have A, B, and C. We're going to have F and S pointing in different directions for each problem. So on part A, F will point up and S will also point up. For B, F will point up, but S will point down. And for C, F will point up and S will point to the right. So if we go to calculate work, it's going to be pretty easy to start. It's going to be 400 times 10, 400 times 10 times cosine theta. So for each of these, all we really need to do is determine theta. And I chose these examples because they're a little bit weird. First of all, this angle is 0. If two arrows point in the same direction, the angle between those arrows is considered 0. So that is a really important thing to know. Two arrows are parallel and they point in the same direction. The theta is 0 for them. So we can easily calculate this now. Work equals 400 times 10 times cosine 0. You might be tempted to say that the answer is 0, but really, if you type in your calculator, you'll see the cosine of 0 degrees is 1. So it's 400 times 10 times 1. Type that in your calculator now. Make sure that cosine of 0 equals 1. If it equals something else, that means your calculator is probably in radians. So work is 4,000 joules for this case. What about part B? Well, two arrows that point in opposite directions are 180 degrees. Very important to memorize. If two arrows are totally opposite direction, theta is 180. So once again, pretty easy calculation. 400 times 10 times cosine of 180. Again, make sure your calculator is yielding a different answer here. Cosine 180 is negative 1. Cosine 0 is 1. Cosine 180 is negative 1. Make sure your calculator is getting negative 1. If you type all of it together, you'll get negative 4,000. So notice, by choosing these arrows properly, by choosing these angles properly, based on the arrows, we get a positive or a negative. Sometimes we'll get decimals if these arrows are like 30 degrees or 50 degrees or whatever. Last one here will be actually pretty easy to calculate. Take a look, we've got a right angle between F and S. So theta is 90. Same equation, same numbers until the last one. So work is 0 joules here. Cosine of 90 equals 0. So it's kind of weird. Over here, we see a 0, so we think this answer is going to be 0. But with trig, it's not always what you might think. So make sure you can identify each of those as 0, 180, and 90 respectively. Apart from that, that's pretty easy, I think. The challenging thing with work, the thing that makes this a challenging concept, is the ability to draw these arrows on your own. I provided these for you, but based on the context of the problem, you need to draw these arrows. So we'll do that in the next example. I'll show you how to do that in the next example. Okay. So in this one, here is, so we're calculating work again. Here's the premise though. Real simple. A 70 kilogram person rides up 25 meters in an elevator with a constant velocity. A 70 kilogram person rides up an elevator, rides up 25 meters in an elevator with a constant velocity. Make sure I'm not missing any information. Nope, that's it. Calculate the work done on the person by A the elevator and B gravity. Let's draw a quick picture too. I believe that'll be all the information on. Okay, a 70 kilogram person rides up 25 meters in an elevator with a constant velocity. Calculate the work done on the person by A, the elevator, and B, gravity. So this addresses one of our weird definitions from early on. The definition that F is the particular force being analyzed. F is not just force, it's a specific force that is doing work. I can calculate the work done by friction. I can calculate the work done by air resistance. I can calculate the work done by anything. So part B is obviously gravity. They want to know the work done by gravity pulling down. And part A is a little bit hidden, but the way an elevator pushes you up is by means of normal force. So when you are moving up in an elevator, it's because normal force is pushing up. Remember, normal force is like a surface force. When you're standing on the ground pushes up on you. That's just what it's called, normal force. Thing to remember about it is Fn and Fg are usually equal in this class. And Fg is equal to mg. So right here, this kind of describes the particular problem we're on. Normal force, Fn equals Fg equals mg, and this is only because no acceleration. If this person were accelerating upwards, that would mean that Fn is larger. If this person were accelerating downwards, that would mean that Fg is larger. But they're moving steady upwards. So although they're moving up, there's a perfect balance between F and N. Unbalanced forces only cause acceleration. So the fact that they're moving constant means that these are balanced. They're moving nicely in tandem. Okay. Let's go ahead and try to calculate. So basically, we're going to need to use this mass. This is m. Take that times 9.8 to get Fn or Fg. Let's try it. Let's give it a go. So this will be a little trickier. Work is equal to force times displacement times cosine theta. Okay. Now I can't just plug in this. I'm going to label that just to emphasize. This is m. Mass, m. So I can't plug that in for F. I need to multiply that by 9.8. I need to multiply that by g to get the force. So what we'll do here is I'll show, just to be really descriptive, I'll show two steps. What is the force that's doing work here in part A? It's the normal force. It's the floor of the elevator, Fn, times S times cosine theta still. But how do I calculate Fn? Well, I type in mass times 9.8, mg. So here is our general equation that is easily solvable now. Let's plug in our numbers. Remember what this problem is all about. I'm going to teach you how to draw theta. All we've really been doing is reviewing so far. I'm going to teach you how to draw theta in this step. Once we get there, it'll be tricky. So here we go. Here's the numbers. W equals 70 times 9.8 times 25 times cosine theta. What is theta? Look at your definition. Theta is the angle between vectors f and s. The angle between vectors f and s. So s is pretty obvious in part A. S points up. I'll draw that in the margins. And what about normal force? Normal force points up as well. So here we have that characteristic shape we saw in our first example. What angle is that? 0 degrees, my friend. So normal force points up, displacement points up. That's an angle of 0 degrees. So our answer is 17,150 joules. Okay, let's look at part B. Part B, same equation, of course. We're supposed to calculate the work done by gravity in part B. I can just show the picture. We want to find the work done by gravity. So work equals F times, you know what, I'm going to write Fg, because that's the particular force that we're talking about here. You don't have to write Fg. Okay, so the work done by gravity is gravitational force times displacement times cosine of the angle between gravitational force and S. To calculate gravitational force, it's right here, it's mg. Mg times S cosine theta. Let's go to plug everything in. Work equals 70 times 9.8 times 25 times cosine, not sure. What is the angle between gravity and displacement? What's the angle between gravity and displacement? Well, I'll draw them to figure it out. Gravity's like this, that's the force. What direction is the person moving? What's the displacement? Person rides up in an elevator. So the displacement is the same as part A. And that is a 180-degree shape. So we'll have the same answer, except it will be negative. So what did we do in this problem? In order to calculate work, first we determined that Fn and Fg are the same thing. We determined that the work done by the elevator is actually the work done by normal force, and that both of these, Fn and Fg, are calculated by 70 times 9.8. That's not going away. That'll be around for a while, the fact that Fg equals mg. More importantly, the number one thing I want you to take out of this problem is this here, the ability to draw these arrows based on the context. Here, on part A, the elevator pushes up, there's a force up by the elevator, and the person moves up. In part B, gravity pulls down, but the person moves up. I'm going to put an S there. The gravity pulls down, but S is up, therefore the angle is 180. So in order to solve these problems, you need to draw S and F. So there's my conclusion. This is my my note, my conclusion for you. Something to know when you're going to solve these problems. In conclusion, in order to determine theta, which is written like this, you need to draw an arrow that represents displacement S and an arrow that represents the particular force being analyzed, which is F. In order to determine theta, you need to draw an arrow that represents displacement and an arrow that represents the particular force being analyzed. In the problem we've just done, S was up for both situations, but F was up or down, depending on the context. That is it. Thanks for watching. Go submit this on Google Classroom. Nothing else to say. Have a good one, everybody.